Okay, I'm really happy, yes, to say that today we have the second lecture in the framework of the mini course given by Professor Tao Feng from Beijing Jiao Tong University. And the title of this mini course is Difference Methods and Combinatorial Design Theory. So today we have the second lecture, which is about difference matrices and something interesting in groups. Okay, the floor is yours.
Okay, thank you, Alina. Thanks for giving me this chance to give a talk on difference matrix. In this lecture, I will not talk too much on details. I just want to see some background and motivation and several known results on this topic. First, let us see what's difference matrix, and I will talk about why I talk about this concept. What's the relation between this concept with difference family? Difference family is my main topics in my last talk 2 weeks ago. Okay, let G be a group of order n. Just for convenience, the operator is written by plus, and k is an integer greater than or equal to 2. A GK lambda difference matrix is a k by lambda n matrix. D is Dij. Dij is the entry of the matrix. It is from the group G such that for any two distinct rows x and y, the list of differences dxj minus dyj, here j runs over 1 to the lambda times n. If the list of this difference set covers each element of G exactly lambda times, then this matrix is called a difference matrix. Here is an easy example. In this example, the elements taken from a cyclic group of order 3, we can check that for any two distinct rows, their differences covers 0, 1, 2, the 3 elements, each element exactly once. So the parameter is Z3, 3, 1. The second 3 means 3 rows. Even though this example is very easy, but we can see a little more. First, we can see that in this example, in the first row, all of the elements are 0. And if in the second row, the element is x, then the third row, the element is 2 times x. And actually, this simple observation can be generalized to a more general example like this. Now we construct a cyclic group of order n k1 difference matrix. It is a matrix consists of k rows and n columns. This is its jth column. The first row is 0, all of 0. The second row is j. J runs over 0 to n minus 1. The third row is 2 times j. Because the first row is 0, so when the other row minus the first row, if it's going to cover all the elements of cyclic group of order n exactly once, then these rows must be a permutation of cyclic group of Zn. So we require n and n are co-prime to the k minus 1 factorial. Okay. And actually, this simple example can be generalized into the following example. It was the first mentioned by Nicol in 1979. Let Rn be a finite commutative ring with identity having n elements. In our above example, we take Cn as the Rn, and let the set I be a subset of Rn, and the size of set I is K. Here in our former example, we take I to be the set consists of the elements 0, 1, 2, 3 to the k minus I. If any difference I1 minus I2 is a unit of Rn, in our example, we require n is co-prime to k minus 1 factorial. Then the k by n matrix, each entry is of the form I times j, I in the set I and j in the set Rn. It will form a difference matrix. Akademgorodok first introduced the terminology difference matrix, but actually this concept appears earlier. I will mention its history later. Here, I just want to emphasize one thing. Akademgorodok introduced this concept. The purpose is to construct a special kind of design named transversal design. Just like I talked about in my last lecture, many kinds of design can be constructed from different families. And actually, this kind of design, transversal design, can be also constructed from relative different families. So here, let us recall the definition of difference family, and then I will see what's the relation between difference matrix and difference family. Let H be a subgroup of group G. A GHK lambda difference family is a family flower F of K subsets of G, such that the multiset dot flower F. This multiset consists all of the possible differences contributed by the base blocks. If dot flower F covers each element of G minus H exactly lambda times, then the family flower F is called a difference family. Okay. A typical standard constructions for difference family from difference matrix is shown like this. If there exists a GK lambda difference matrix, a difference family, and an HK mu difference matrix, then there is a difference family with this parameter. Here, 1G, the second parameter 1G is the identity of the element G. The proof is easy. First, let flower F be a GK lambda difference matrix, a difference family, and D be an HK mu difference matrix. And we take any base blocks F from the difference family. Its elements consist of F1, F2, Fk. And then we construct a K set, capital C, Fj, like this. Each element consists of two coordinates. The first coordinate is just F1, F2, Fk. And the second coordinate consists of the columns of the difference matrix. So the jth column, the first element is D1j, the second is D2j, dkj, okay. And then it is readily to check all of the collections of the capital C, Fg forms difference families as we desired. It's easy to check because the first coordinates forms a difference family. So all of the difference contributed by them covered the all of the non-identity elements of G. And the second coordinates coming from a difference matrix. So all of the difference will cover the elements of H. So it's easy to see that we have different families as we desired. Okay. This construction first appeared in John Nichols' paper. Yeah, actually, in the literature, there are many recursive constructions on difference family. Most of them are variations of these simple constructions. But of course, some variation is a little complicated, but the basic idea almost the same. Another simple example on difference matrix is a G2-1 difference matrix. Clearly, it always exists because we can construct a 2 times the size of G matrix such that the first row consists of all 0 or all the identity of G, and the second row consists of a permutation of G. Clearly, if there is a GK1 difference matrix, then we can move any row from this matrix to form a GK-1 difference matrix. So the fundamental question on difference matrix is how to construct the difference matrix with as large as possible number of rows. Dragonico showed that the number of rows is no more than lambda times the size of G. And does this upper bound is tight for some cases? Yes. For example, the multiplication table of the finite field of order Q forms a difference matrix. Here, the group using the addition group, or it is the elementary group. It's easy to check. Actually, when K attained the upper bound, K equal to the lambda times the size of G, a GK lambda difference matrix in the literature is often called a generalized Hadamard matrix. What's the relation between this matrix and the classic Hadamard matrix? A classic Hadamard matrix of order M is an M by M matrix in which every entry is 1 or minus 1 such that each times the transpose of H equal to M times identity matrix. And we can check these facts. A Hadamard matrix of order 4 times n is equal to a generalized Hadamard matrix, and each element is defined on the group of order 2. That is to say 1 or minus 1 are the two elements of the group. And the multiplication 1 times 1, 1, minus 1 times minus 1, 1, 1 times minus 1, minus 1. It's easy to check. It is equivalent. This is because, for example, we can check how to get this observation from left to so that means the difference contributed from any two differences will have the same number of 1 and minus 1. So here the index lambda is 2n. It forms a generalized Hadamard matrix. Okay. Similarly, the other way can obtain this. We know that the Hadamard matrix existence is far from being solved. Hadamard conjecture that there is a Hadamard matrix of order 4n for any positive n. And in this talk, I actually don't want to talk too much on Hadamard matrix or generalized Hadamard matrix. I just want to see why difference matrix is an interesting topic, and you will see this concept are closely related with many interesting topics in combinatorics. Here is one example, and If you want to learn more on generalized Hadamard matrix, you can refer to the survey by Delaunay in the Handbook of Combinatorial Designs. And in this survey, Delaunay listed many conjectures. Okay. Here, I want to see more on the original motivation on why people are studying different matrices. This concept was first explicitly used by Bose and Bush using different terminology, not this terminology. Just I said, this terminology was first given by Nicol in 1970. Bose and Bush are famous statisticians. So they use this concept to construct orthogonal arrays of strength 2. Actually, orthogonal arrays are equivalent to some concept on Latin squares, especially orthogonal Latin squares. So actually, the concept on difference matrices can be found more work in Mann's work in 1940s. As a summary, the original version on studying difference matrices is to construct transversal designs. And actually, this design are equivalent to orthogonal arrays. Orthogonal arrays are equivalent to mutually orthogonal Latin squares. In the following, I will see more on Latin squares because for most combinatorics, Latin squares is more friendly. So I will use Latin squares to illustrate what's the relation between difference matrices and Latin squares. First, let us recall the definition of Latin squares. Latin square of order n is an n-binary array in which each cell contains a symbol from an n set, such that each symbol occurs exactly once in each row and exactly once in each column. For example, here, this is Latin squares of order 3, and you can check the definition. Of course, the basic question is, does a Latin square exist for every positive integer n? Yes, because it's easy to construct them. The multiplication table of any given group can form a Latin square. So a further question is, does it possible to construct orthogonal Latin squares? What's orthogonal Latin squares? A pair of n by n Latin squares are called orthogonal if one will superimpose them. Superimpose means place one on top of the other, such that each of the possible n-square ordered pairs of symbols occur exactly once. And here is an example of a pair of Latin squares of order 3. One can check that all the pairs 0, 0, 0, 1, 0, 2, 1, 0, 1, 1, 1, 2, 2, 0, 2, 1, 2, 2, all of the 3 possible pairs occurs exactly once. A transversal of a Latin square of order n is a collection of n cells which do not share a row, a column, or a symbol. In our last example, we observe the right Latin square of order 3, the right one. We can see the 3 blue elements, 0, 1, 2, the 3 blue elements forms a transversal of this Latin square because they lie in different rows, different columns, and they are 3 different elements. And similarly, the 3 red one forms another transversal, the 3 black one forms another transversal. So Euler in the 17th century asked, is there a Latin square of order n whose entries can be partitioned into transversals? Actually, Euler's problem is equivalent to asking, the existence of a pair of orthogonal Latin squares. In our above example, in the right Latin square, the three blue elements 0, 1, 2, we can observe their corresponding elements in the left Latin squares. They are 0, 0, 0. So the three pairs 0, 0, 0, 1, and 0, 2 appears. And observe the right Latin squares with red elements 1, 2, 0. And we observe the left Latin squares. Their corresponding elements are all 1. So 1, 1, 1, 2, 1, 0. These three pairs appears. Similarly, the black one. Anyway, okay. Euler's problem is equivalent to ask the existence of a pair of orthogonal Latin squares. This problem was solved in 1960s. The answer is yes, but n cannot be 2 and 6. A further question is, can one construct more Latin squares such that any pair of them are mutually orthogonal, and let n be the largest number of Latin squares of order n such that they are mutually orthogonal. It is easy to get this upper bound. The value n is no more than n minus 1. And when n is a prime power q, it is easy to show that the upper bound can be achieved. But the question is there any other elements such that n equal to n minus 1? A famous conjecture is this upper bound can be achieved if and only if n is a prime power, and it is famous that this conjecture is equivalent to ask the existence of finite projective planes. So it's a very hard problem. Anyway, the study on the number or on the value n at least divides into two directions. One direction is improve the lower bound. For example, the solution to Euler's problem use the fact that the number of n is greater and equal to 2 for any n is not 2 and 6. Another direction is to analyze the asymptotic behavior of the number of n. In 1960s, Erdős, Czola, and Strauss give a result. Their result showed that the number of n is greater and equal to 2, n to the 1 over 91. And after Erdős' work, many people try to improve their lower bound. And maybe the best lower bound so far is this one. The 91 has been improved to 14.3 here. Of course, the purpose is to make the value as lower as possible. It's an interesting problem. Actually, the technique to improve the lower bound will use sieving method in analytic number theory. Okay, anyway, here we see what's the relation between difference matrix and mutually orthogonal Latin squares. And GK1 difference matrix is equivalent to a set of k minus 1 mutually orthogonal Latin squares based on G. And these Latin squares are obtained by permuting the columns of the multiplication table of G. Now we give a quick looking at the proof. Here we just see how to prove this proposition from left to right. Okay. First, let D be a GK1 difference matrix. Without loss of generality, the first row of this matrix can be always written as identity of the group. This is because, for example, this number, for example, is G3. So then we can let this column, each element minus G3, such that G3 be 0 or the identity. This operation will not change the differences. So anyway, without loss of generality, for any difference matrix, we can let its first row is identity of the matrix. And similarly, we can let the first row is also the identity of the matrix. For example, if this matrix is G4, and then we can let all of this row's elements minus G4, such that this element is the identity. Okay, and this will also not change the difference between these rows and other rows. Anyway, a difference matrix are determined by all the rows except the first one. Now we want to construct k minus 1 Latin squares. And each row from the second row will contribute an Latin square. For example, we want to construct a Latin square from the second row. Because the first row is identity, so the second row will be a permutation of the group G. So now we can construct a Latin squares using the multiplication table of the group. The table can be made as follows. First, we label its rows by the element of the group, and then label the column by the second row of the difference matrix. Then clearly it is a Latin square. Similarly, we can, from the third row of the difference matrix, form another Latin square, and blah, blah, yeah. And finally, we need to check all of the Latin squares are mutually orthogonal. I will omit the mutually orthogonal checking. Okay. Anyway, I believe you have the image on the relationship. Okay. This simple proposition shows that if we want to construct mutually orthogonal Latin squares, then you can first try to construct a difference matrix. In the literature, most of the best known lower bound on the value of n with n is a small value coming from the construction of difference matrix. Okay, and actually in recent years, Apple did many good work on this problem. Okay. In the following, I will talk another concept, also orthomorphisms of a group. Actually, this concept is very, very closely related to difference matrix. A bijection theta from G to G of a finite group G is an orthomorphism of G. If the mapping X2, the inverse X times theta X is also a bijection. This concept is a little complicated when we first look at it. Actually, it is nothing but a GK1 difference matrix. Okay, now we construct a GK1 difference matrix as follows. First, the matrix first row consists of theta x. According to the definition of orthomorphisms of G, theta is a bijection. So theta x consists of the third row. It's a permutation, okay. And when we count the differences from between the third row and the second row, so we need to count theta x minus x. And according to the definition, the mapping theta x minus x is also bijection. So that's why I said orthomorphisms of G. So this concept is equivalent to the existence of G31 difference matrix. They are equivalent, yeah. And a related concept is named complete mapping. A complete mapping of group G is a bijection row from G to G such that x to x times row x is also bijective. Here, the difference between this concept and the above concept is only here is x times row x, and above is the inverse x times theta x. Actually, these two concepts are equivalent because essentially the map G to the minus 1 is also a bijection. So in not too much literature, but indeed there's some literature. They use any definition to define orthomorphisms of group. Okay. Two orthomorphisms, theta and phi of G, are orthogonal if the mapping x2 theta x to the minus 1 phi x is also bijection. Actually, this concept is equivalent to G41 difference matrix. We can construct a G41 difference matrix such that its first row consists of all the identity of the group G. The second row, x. The third row, theta x. The first row, phi x. And theta and phi are bijection. So each row except the first row are permutation of the group G. And theta x minus x and phi x minus x, phi x minus theta x, according to the definition, they are also bijection. So indeed, it's a G41 difference matrix. Furthermore, clearly, K pairwise orthogonal orthomorphisms of G are equivalent to G K plus 2,1 difference matrix. We have known that a difference matrix with 2 rows is trivial. But how about the existence of difference matrix with 3 rows depend on any given finite group? It's not easy. Hall and Paige in 1955 made this conjecture. It says a finite group G admits a complete mapping, or using our terminology of difference matrix, it says if there exists a G31 difference matrix over a finite group G, if and only if its CO2 supergroup of G is either trivial or non-cyclic. Hall and Paige in the same paper proved this conjecture when G is solvable, and we know that any group of order is solvable. So that means for the existence of difference matrix with 3 rows has been solved. And Wilcox reduced the Hall-Paige conjecture to the case of simple groups. We know that a finite simple group is one of the following: a cyclic group of prime order. So it's solved because it is odd number. An alternating group. In the same paper, Hall and Paige solved the case of alternating group. And a group of Lie type and 26 sporadic groups. And for the remaining cases, Wilcox in 2009 gave a unified construction for groups of Lie type, leaving only the Th group and the 26 sporadic groups. And in the same year, Evans checked all remaining cases and left only one possible exception, the fourth Junko group. And this last exception actually was solved in the same year by J.N. Bray, but he didn't publish his results in any paper at that time until 2020. Bray、齐蔡、彼得凯门人、Spiga、华章 they investigate the synchronization for affine and diagonal groups using the Hall-Paige conjecture. So in this paper, they include Bray's last case on the fourth Junko group. So that means the existence of G31 difference matrix was finally solved, or that means the conjecture by the Hall and Page was finally solved. A natural question is, how about the existence of difference matrix with 4 rows? Of course, the basic case is how about the matrix defined on the cyclic group? It's not easy, actually. Evans developed an explicit construction for a pair of orthogonal orthomorphisms. Okay, just as I said, a pair of orthogonal orthomorphisms, this concept is equivalent to the G41 difference matrix. Okay. And he cannot solve the case V is 9 modulo 18. 2 years ago, my PhD, Meng Long Zhang, and my academic sister, Xiaomiao Wang, we give a direct constructions for this last case. And so this solves all the cases over the cyclic group. Why this case is difficult to construct? The reason is the order 9. When V equal to 9, there is no pair of orthogonal orthomorphism. In design theory, a typical approach is to establishing some recursive constructions. And so these constructions will heavily rely on the concrete examples. So because the order 9 does not exist, so people cannot using the recursive constructions to finish all the cases of the value V is 9 modulo 18. And why people are interested in the cyclic difference matrix? Cyclic difference matrix means this matrix defined on cyclic group, because this kind of matrix have many applications in combinatorial coding theory, such as optical orthogonal code, optical orthogonal signature pattern code, geometric orthogonal code, frequency hopping sequences, and comma-free code. So that's why we are interested in the cyclic case. Okay. Actually, our construction is very simple. Okay, it's a direct constructions. Now we want to construct a difference matrix with 18 times t plus 9 columns. All the columns are divided into 2 parts. The first part consists of 18 times t minus 11 columns, and the second column and the second 20 columns I omitted from my slides. Okay, I just list the first 18t minus 11 columns. Actually, this column has some pattern. Okay, let us recall our first definition, the very simple definition. For example, this column, the first one is 0, I, 2 times I, 3 times I. We know that if all of the columns have this form, then the order must be co-prime to 6. But here, the order is 18t plus 9. So it does not satisfy the basic condition, but we just use this idea, not exactly the form of this one. So the first column is 0i, 2i, 3i. The second column is 0, 6 times t plus I. And actually, this number times 2 is almost this number, 12t plus 2i. Plus here not 8, it's 6. And the third one, 1 plus 3i, is 3 times this value, 6 times t plus I. 6 times t is 18t. 18t is 0. Okay. So that means actually we almost use the standard pattern of the column, but we did a little modification. It's a little surprise. We succeed. Okay. So a further question is, how about the existence of a G4 lambda difference matrix over any abelian group? And for any abelian group in 2016, Rong, Pan, and Yan Xunchang, they solved all the abelian cases except for the cyclic case. So combining their results, we complete all the cases over abelian groups. And furthermore, how about the non-abelian case? Of course, the simplest cases. The simplest case to check, to examine, is the dihedral case. And we check the case for the generalized dihedral group, and we solved its necessary conditions is also sufficient, like you see here. Okay. Of course, a more interesting problem is how about the general case? I mean, because Hall and Paige conjecture has been solved. So how about the case for the K24 for other groups? First, we have a simple theorem. This theorem says let K be an integer. Then there exists a GK1 difference matrix for any finite group G satisfying the size of G is co-prime to K minus 1 factorial. I believe you are very familiar with this condition. That means the proof is very similar to our first example. The idea is very simple. Okay, we look at this proof quickly. Okay, let D be a K by N matrix with the jth column like this. The first element is 1, second Gj, the third Gj square, Gj K minus 1. Okay, this is its jth column with the standard pattern. Then D, this matrix D, is a GK1 difference matrix if and only if the mapping G to the R is a bijection from G to G. And since N and R are co-prime, so the concurrent equation Sn plus 1 is 0 modulo R. There is an exactly one solution. Hence, for any G in G, G can be written as this one, which implies that G to the power R is a bijection from G to G. So the proof is very, very simple. Actually, I don't know who first gave this proof. I checked many references, but I didn't find the explicit statement on this theory. But in Brady's paper in 1998, he mentioned this result, I colored blue. Okay. He said, if G is a finite group and K is the smallest prime factor dividing the size of G, then there exists a GK1 difference matrix. It's easy to see that his result is equivalent to the above theory, but he proved this result using the fact that any group of odd order is soluble. But our proof is very elementary. So I checked the literature more, and I found in Evans' book in 2018. I will list the book later. Okay, later in later slides. Okay. In this book, in his theorem 8.14, Evans gives the same result as Brady, colored blue here. Actually, Evans' book, even though published in 2018, actually this is his second edition. The first edition appeared in 1993. So in 1993, this result has been known. But anyway, I still don't know who is the first one give the Bob theorem. I think the Bob theorem is very important to consider the generalization of Hall-Paige conjecture. Okay, so when k equal to 4, for our purpose, this simple theorem showed that when the size of G are co-prime to 6, then the existence solved. Okay. So, okay, actually, I'm trying to do this problem, and the above theorem I just told you is only I observed this fact 3 months ago. Okay, and recently one of my PhD, Shikang Yu, and I completed the case for the finite P groups. Specifically, when P is greater and equal to 3 or prime, we can show that a difference matrix with 4 rows over any such finite P group always exists, except for the cyclic group J3 and J9. And when P equal to 2 for the finite P group, and the necessary condition is also sufficient. The necessary condition is whose CO2 subgroup either trivial or non-cyclic. This is the basic necessary condition. Because if a G41 difference matrix exists, then a G31 difference matrix exists. G31 difference matrix is a Hall-Paige conjecture. So in their conjecture, there is a necessary condition. Okay, this is their necessary condition. Of course, a natural problem is how to consider other complicated group. The same recently, okay. I think my students, you and I, can solve the case for nilpotent group, for any finite nilpotent group, because nilpotent group finite is product of a finite P group. I think we can finish it before this summer. But how to solve the cases on all the cases of solvable group? So far, I have no idea. Just I said in 1955's paper, Hall and Page had solved the conjecture for the solvable group. But why I cannot do it so far? So we need to check their paper. And in their paper, we cannot generalize this recursive construction. Actually, this is a recursive construction. We can generalize it from 3 rows to 4 rows. Anyway, I will do not talk too much on this remark. I just mentioned this remark if someone interested in this topic, and you can see the paper. Okay. This is a difference matrix with 4 rows. The next question is how about 5 rows? Of course, it will be very complicated. Many people here, including Apple, and just I showed you, Apple are very good at constructing a difference matrix, and he constructed many difference matrices to construct mutually orthogonal Latin squares. Okay. So he and his PhD students helped us to construct many concrete examples, and together with some recursive constructions, we obtained this result. This result means for any finite filling groups, the equations are solved except for these 3 cases. In the third one, means the cyclic case still open. 1G is isomorphic to cyclic group of order 9 times P. This case is still open. Here, P is an odd prime. So because P is odd prime, so 9 times P is 9 modulo 18. That means this case, okay, C 18 times T plus 9. This case is still open. Because we give a direct constructions for the same parameter with 4 rows. So a natural question is how about we use the same technique to solve the 5-row case. But we failed. We didn't succeed. But we can construct an almost difference matrix. Almost means a difference packing. Okay. We need to construct 18T plus 9 columns, but we only construct 18T plus 5 columns. We couldn't add the 4 more columns into it. We use the same pattern. Okay. Of course, a question is whether it is possible to change another pattern. In our another paper on the existence of group divisible designs, we construct 2 Z741 difference matrices up to isomorphism. We find these 2 matrices. One has pattern 0I2 I3I, another has pattern 0I2 I4I. They are not isomorphism. They are not isomorphic. So I don't know whether maybe in our array, this pattern are not good. Maybe we can try another one. I don't know. Okay. Of course, here an interesting problem is do some classification for difference matrix. In the literature, not too much paper on these topics. Okay, it's a possible direction. And another question is, can we construct a GK1 difference matrix with a given small value of K for any possible group G? So in the literature, I mentioned Evan's book in 2018. Okay, just this book. This book is a very excellent book if you want to learn this topic. Okay, in this book, there is a chapter to list 1G is small when the size of G is smaller than 16. And what is the largest possible number of K? It's solved. So when the size of G is 16, this paper didn't finish all the possible cases. So we did some computer search work. For example, we can show that no Q1651 difference matrix exists. And we can find some G51 difference matrix for G belongs to D16 as D16 or M16. Okay, blah, blah. Anyway, another interesting question is do some computer work. I believe there will be need some clever search method, okay, to search what's the largest possible number of rows for the small group G, okay. Another interesting problem is consider asymptotic existence. Why I mentioned this topic for 4 rows? Actually, there have been several papers just very recent years for 3 rows. Eberhard, Manners, Marjovich in 2020, they used non-abelian Fourier analysis and circle method from analytic number theory to establish the asymptotic existence of G31 difference matrix. Actually, they did more. They give actually they give the number of such matrix. We know that if the number is greater than or equal to 1, it exists. Okay. I mean, they discussed the number of this matrix. Okay, they did more. And Mil-Yeser, Pokrovsky, okay. They established another stronger result in 2020. It seems that this paper it is still in archive, okay, not published in some journal, okay. Okay. They consider this problem given equal size subsets A, B, C of a group G. Is there a bijection phi from A to B such that psi A to C defined where psi A is A times phi A is also bijection? Maybe it's a little confused. For example, we take A, B, C is are the group G. A is G, B is G, C is G. Okay, then we see it's their statement. Is there a bijection phi from G to G such that psi from G to G defined by A times phi is just bijection? So when the subset ABC are G, their question is the same as the existence of the complete mapping or orthogonal of groups or G31 difference matrix. Okay. So their question is a generalization of the traditional problem. So that means they give another proof on the asymptotic existence of G31 difference matrix. Their truth is the absorbing method. And last year, okay, the first author, Muyesser, and considered the following conjecture. He showed the following conjectures holds for any sufficiently large abelian group. Okay, what's the conjecture? This conjecture. Okay. In 1981, FGT, these 3 mathematicians conjecture that when G is abelian for any K divides size of G minus 1, there is an orthomorphism of G fixing the identity and permuting the remaining elements as products of disjoint K cycles. A little confused, so we give an example. Here is an example on J931 difference matrix. The first row are consist of 0, so I omit the first row. Okay. The second row is permutation of J9. The third row is permutation of J9. Okay. When we just focus on these 2 rows, it can be seen as a permutation. And this permutation can be written as a product of disjoint cycles. So for this example, 0 from 0 to 0, from 1 to 2, 2 to 1. So this is 2 cycle, 2 to 6, 6 to 3, 4 to 8, 8 to 4, 5 to 7, 7 to 5. Okay. So this example gives the existence of J9431 difference matrix. Of course, we can ask more. Okay, we can find another example. For example, in this example, we can check it is a difference matrix as we desired, and the permutation can be written as 0 to 0, 1 to 3, 3 to 2, 2 to 5, 5 to 1, and 4 to 8, 8 to 6, 6 to 7, 7 to 4. Okay, and another example. And this permutation can be written as 0 to 0, 1 to 2, 2 to 5, 5 to 3. Anyway, it's a cycle of length 8. Okay, so now we read the conjecture. Again, the conjecture side, 1G is abelian for any K divides size of G minus 1. There exists an orthomorphism of G, fixing the identity and permuting the remaining elements as products of disjoint K cycle. So that means this conjecture is a stronger conjecture than Hall-Paige conjecture. Okay. Just I said, okay, the Musser and that for all sufficient large abelian group, this conjecture holds. The method is still absorption method. I mentioned this conjecture, this work, because I think they are interesting tools in design theory. We know recent years there are many asymptotic work, but most work focus on structure without algebraic structure, focus on configurations without algebraic structure. So these papers focuses on configurations with strong algebraic structures. So I think maybe this technique can be used to generalize maybe to other cases. Yeah, I think they are interesting. So I talk about it. Of course, maybe you will ask, here, we know in the above example, of course, we can see, does it possible to find a permutation with the type, for example, 0 to 0, 1 to 2, 2 to 3, 3 to 4, 4 to 5, a cycle of length 5 plus a cycle of length 3, 5 plus 3 plus 1, 9. Yeah. So there are many other cycle types. So is it possible to form a G31 difference matrix with any given type? Okay. In the literature, there are some papers, okay, discuss this. Here, I just list one of them. Okay. It's discuss the cycle types of continuous mappings defined over the finite fields. Okay. Finally, I talk about another generalization of difference matrix named a generalized Bascar-Roll design. Bascar-Roll is a name of someone, a person's name. This design is an M by B array, each entry of which is either infinity or an element of the group, such that each column has exactly K group element entries. And for any two distinct rows X and Y, the list of differences dxj minus dyj. Here, if dxj or d minus j is one of them is infinity, then we omit the differences. Okay, we didn't count it. We don't count it. If the list contains each element of G exactly lambda over times G times, then this design is called generalized Bascar-Roll design. Here, maybe you are strange why here require lambda over the size of G. It's a little strange because this design was first used to construct balanced incomplete block design. Okay, and the corresponding parameter is such kind of GBRD can use a BIBD. with index lambda. So just for convenience in the BIVD, so here the definition defined as lambda over the size of G. Okay, it's not important. Okay, it's not key. 1 m equal k. According to the first condition of the definition, the first condition requires each column has exact k group elements. 1 m equal to k, m means m rows. So that means in the rows, the infinity cannot appear. So in this case, a GBRD is just a difference matrix. They are equivalent. So this concept is a generalization of difference matrix. Actually, from the aspects of design theory, this concept is very, very natural because difference matrix corresponds to transversal design. Transversal design is a special type of group divisible design. So GBRD can yield a group divisible design. So from design theory, it's natural to require to ask the existence of GBRD because it is equivalent to such kind of group divisible design. And what's the main meaning of the generalized in the terminology? Okay. When the group G is of order 2, a GBRD is called a Baskerville design. This is the design first given by Baskerville in 1966. Okay. If you want to learn more on this topic, you can find the handbook of combinatorial design theory. But the book was written in 27, and after 27, there are some many other results in literature. So I list this paper because in this paper, most known constructions and most known results were collected. I don't want to read it. This is my slides of this lecture. And actually, as a remark, okay, I mentioned one thing. In this lecture and in my last lecture, these difference methods are used to construct two designs. In the last lectures, two cyclic two designs. In this lecture, cyclic or semi-cyclic or something like that, group divisible design. There are two designs. How about three designs or T designs? How about construct them using difference methods? There are many literature to discuss them. For example, for difference matrices, it is only for two design. One general case T design, there is another name in the literature named difference scheme. Okay, actually, difference scheme is a generalization of difference matrix. And in some literature related on coding theory, the difference scheme was named as simple matrix, R simple matrix. Okay. Anyway, actually, I mean, they are totally equivalent. They are all the generalization of difference matrix. The purpose is to using this concept to construct T designs with some specific orthomorphism group. Okay. Thank you.
Dear Tal, thank you so much for your talk. Well, are there any questions to Tal?
Yes, I have a question.
Oh, yeah, sure, please, yeah.
My question is about orthogonal arrays. Do you know construction of orthogonal arrays with strengths greater than 2, which were based on difference matrices?
You mean construct some orthogonal hyperlatin squares, similar like that?
Not Latin square, but Latin cubes.
Latin cube.
Latin cubes.
Okay. Yeah, it's a good question. Yeah. Yeah, I think there is there are some natural correspondence between Latin squares or Latin cubes or something like that to the specific structure of design theory. In the I think I guess
Okay.
I guess your questions are closely related to the existence of transversal designs.
Yes.
Yeah, transversal design here, I mean the T transversal design, not the T22. Okay, T is greater and equal to, yeah, means T design. And in the literature, for example, when T equal to 3, there are some known results on the transversal designs, T to 3. So I think it will correspond your cubes. Yeah, I think so. Yeah.
Thanks.
Okay, any other questions? Oh, you mentioned about classification of difference matrices. Do you have any ideas how one can do this, actually?
Sorry?
Well, you just, during your talk, at the end of your talk, you mentioned about classification of distance matrices. So, I mean, what is the basis for this? What is for this kind of classification?
Sorry, I'm not very clear your point. Yeah.
Well, actually, at the end of your talk today, you said that you mentioned about classification of difference matrices, right? Yeah. So what did you mean when you talk about this? Yeah. Is it necessary to, well, so some necessary conditions or sufficient conditions, or just to classify all possible difference matrices? Yeah, okay. It seems to me that it's a stupid question. Yeah, okay. Yeah, could you please show the slide number 23? So there is a theorem, and it is shown that it is not done for the case when p is equal to 109. So what is the main difficult? Well, I mean, yeah, in this theorem, yeah, the third case.
Yeah. Because we can construct some concrete examples using computer, and actually
you use computational experiments. Yeah.
Yeah, actually, just I said, Apple are very, very good at to do it. He told me he has he can use his university's computers, and this project we did maybe at least 1 month, okay, around 1 month or maybe 1.5, and it was during the Christmas day, so he said he can use all of the computer machines in his
Mhm.
university. And he said, maybe for me, his computer work equal to my laptop's work 5 or 6 years. Okay.
I see.
Yeah.
Yeah, that is, good approach. And the same should be done when you have got this results, which is shown on the page number 16, because the case, so there are also slide number 16. So there is a theorem with the result, and there is a case when we, where is it? Yeah, so, V is not equal to the set, so it is not equal to 3 and 9. So how did you get this one? So did you use also computational results, or is it theoretical one?
It's easy to do it by computer. No, actually, these two values are known, were known, not exist in 20 years ago, in Akademgorodok's paper. In his paper, he said he obtained them by computer search. Okay.
By computer searching, okay.
Yeah.
So also by computer searching.
Yeah, but I believe it can be dealt with by hand. Yeah, the case will not be complicated. Yeah.
Mhm. You mean to construct exact example, or?
Yeah, I mean, we can do some without loss of generality assumption, then divided some cases, and then analyze them, and then finally there will be some contradiction. Yeah.
I see. Now I do understand. Okay. Now I do understand. Okay. Thank you so much. Yeah. Are there any other questions?
I have one question about the size of the difference matrix. You have a slide with sides of difference matrix for order 12, order 15. If order 12, then the number of rows is 5. If the order of 15, then yes, this. Okay, this slide. My question is this result is strict or not? Maybe greater the difference matrix for large order or not?
You mean how they construct it, or what's the tricky? Or what's the technique, you mean?
I know my student calculate that the first result is strict by complete solvent all permutations, but for other I don't know.
Actually, before I co-authored with Apple, I'm also very curious how Apple constructed many such concrete examples. But after I collaborated with him, I know a little his idea. one of his idea is to use some specific orthomorphism group. Okay, for example, he wants to construct a matrix with 40 columns. Maybe he can design a very clever orthomorphism such that one can construct 8 columns. Then each column generates 1 or 5. Then he finally finds the 40 columns. This is one of his technique. Another technique is he can translate the existence of different matrices to some combinatorial designs. And in design theory, there are some typical method to deal with that those typical design. So if you are interested, maybe you can okay, you can find this paper. Okay. Actually, when we first submitted this paper to DCC, and the referees asked the questions to us. At that time, in this paper, we didn't write too much the ideas behind these examples, but because the referees asked, so I wrote them. So that means in our first edition, submitting to this journal, I will cite it is not necessary to write the details on how to obtain this example, but because one referee cited, so he didn't like write it. I wrote them finally. So I think if you are interested, maybe you can refer to this reference. Yeah.
Okay, thank you.
Thank you.
Yes, thank you very much. Are there any other questions? Well, I'm sure that in nearby future, maybe there are some other questions appear. So is it possible for listeners to communicate with you and contact with you by mail, say? Is it possible?
Yes, it's possible.
Yeah. Okay, it is possible.
Welcome, anyone. Email me.
Yeah, sure, of course. And I'm kindly asking you to send me presentation of this talk, which will be available on the website, so everyone can watch your lecture and read your presentation carefully, because actually today you gave us a lot. I mean, you explain us details about this theory, and you also gave us a lot of good, very interesting references. And actually, you show us some open problems on this area. So thank you so much. I enjoyed a lot. Yeah, thanks a lot. Yeah, thank you. So I think that we finished with these 2 excellent lectures. And the next mini course will be given by Andrei Titenov. Soon I will send some information about this new course. Thank you so much, Tao. Thanks a lot. Yeah.